And something that is important to measure is latency. Latency is the time between events, typically measured as the time from request to completion. It's important because it's a primary measure of application pain. That's when measured as a synchronous component of the workload. So for example, for a MySQL query, if I'm able to measure latency as a component of the query time, it is a primary measure. It's a linear measure of pain as well, such that the higher the latency is, the higher the level of pain is. This is something interesting. It's also ideal. It's not something that you can say about many other metrics. For example, if I'm looking at disks and I'm trying to understand disk IOPS, I can't compare IOPS from one to the other. So is 1,000 IOPS better than 100 IOPS? 1,000 IOPS could be sequential and really fast. 100 IOPS could be random and slow. And it's the same for to a lesser extent, but for throughput as well. If I'm looking at throughput metrics, that could be throughput that is more expensive to perform or less expensive in terms of time. If you can express the performance metric in terms of latency, in some ways as a common currency to convert things to, latency allows you to compare between different sources as well. So if I was to, and to further that example, if I was to try and compare 100 disk IOPS to 100 network IOPS, these are apples and oranges. They're different items. However, if during a query I spent 100 milliseconds waiting on disk I/O and 10 milliseconds waiting on network I/O, I can compare those two metrics. Someone told me that time was the only scientific metric that we use in computing. All the other ones we invent. So we invent IOPS and we invent bytes and bits. Time is definitely useful in terms of latency. If you can convert different types into that synchronous latency, it does allow you to make comparisons. Fetching latency from arbitrary points inside an application is easy to get with DTrace, either event by event or with summaries, whatever you need to answer the question. To illustrate this is what it can look like for event by event latency. Here I'm running a DTrace script I wrote called iosnoop. iosnoop's actually available on Mac OS X now. You can, if you're the root user, you can run it. I've run it with a few options. It's showing each disk I/O event one by one. It's telling me the time in microseconds when that disk event started, the time in microseconds when the event ended, the time from start to completion, the disk time from the previous event to the current event. So this can actually be thousands and thousands of lines per second. If you'd like to understand latency event by event, you can do it with DTrace. I can print out everything and then I can sort on one of the timestamp columns and then figure out exactly what happened. That's one way of us consuming and understanding latency, is just printing out every single event and then sifting through it. Of course, there's other advantages here. I could feed it into other tools and post-process it, look for various things. While all the information is there, it is difficult to identify longer-term patterns because there's just screenfuls and screenfuls of data. I do use this as a last resort. I try to use other summaries first, but sometimes I will have to go to event by event and just look at what happened one by one. Just to illustrate it, we can also present latency as an average. And usually this will mean you're looking at the average latency per second. So this is my average query latency drawn over time. These are all different tools. You pick and use them where appropriate. This is great because it means some patterns are much more visible. I don't need to read through thousands of pages of output. But there are some downsides to this as well. For example, outliers are hidden. A lot of the production MySQL instances I'm looking at what we're trying to chase down is why there are slow queries. So a slow query meaning a query longer than a second. And these production MySQL boxes are usually doing 5,000 queries a second, and there might be one slow query. If you take the average query time, that one slow query is only contributing 1/5,000th to the average that you see, which means it often gets rounded out. So you can't actually see that you've hit outliers, just a few occasional slow queries, because the vast majority of queries are fast, and you've just rounded them down. So in those terms, this average latency doesn't work so well. You can also plot another line for maximum latency, so that you could pick the existence of those slow queries. But then there are other forms of the distribution that get lost as well. So it does help for longer term patterns. For the average, things will get rounded off. Something else that's a bit strange about it, just this graph, this example graph I've printed here, you can see one thing that this has done very well, and that is it's identified this periodic event. So whatever that is, every 10 seconds, our average latency goes up. What does it actually mean? If this was queries, if I was doing 5,000 queries a second and my average latency goes up that much, it means all those queries are so much slower, or there's quite a number of queries that are dragging it up. What if instead, at this point in time, there was only one query? For whatever reason, here we're doing 5,000 queries, and here we only do one query, and that's the time for one query. It's really actually hard to understand what this means because we don't have the count as well. So some people try and solve that, so they'll have the average, and then they'll have the count of events as well as a separate graph. They might have another line here for the maximum. At some point, you might realize that summarizing it down to a single number or a few numbers as a line graph is taking it too far. Latency is a really important metric, and we don't want to throw out this information. And so something that I've done a lot of, and we're doing at Giant, is we're presenting latency as a heat map so that you can see the entire distribution of latency over time. This is also called a column quantized visualization. How this works, on the x-axis is time, and you'll see this clicking along. On the y-axis is latency. So, in fact, it's much better if you actually see it because we have time on two axes, and that just makes it a little bit difficult to comprehend. So here's this is a heat map out of the Giant Cloud Analytics. I'm not looking at MySQL latency in this one. I'm actually looking at the time spent on CPU. But you can see that it's scrolling to the left each second. I'll just zoom out a little bit. Oh, there's some interesting events. So this is the overall time. On the y-axis is the sub-second time for each of these events, where the higher up the y-axis, the slower that event was. It's not a scatter plot. What it's actually doing is it is quantizing the events into buckets that we can, so I can change the size of that bucket, where the darker the pixel is drawn, the more events were in that XY location, which can help pop out various patterns that you may not quite see with the scatter plot. This heat map I've got right here is actually more interesting than that live one in terms of MySQL, because this one is MySQL query latency. So there's the time on the x-axis. There's about 5 minutes as presented here. On the y-axis is the query latency. This goes to 100 milliseconds. I'm sorry, there's no axes drawn here at the moment. This came from a prototype tool that we're developing. And by using the heat map distribution, a lot of detail pops out. So for example, we can see that there are a lot of queries that are fast, that have a low latency, which are going to be between 0 and 1 milliseconds. But there's this wave of queries that are slower, and the pattern is changing over time. Not only that, but there seems to be different bands or levels of latency. I know that at this level, that's 10 milliseconds. So there's a number of queries that finished around that time. And then there seems to be an echo at 20 milliseconds, 30 milliseconds, 40 milliseconds, and so on. It happens again, and then when latency, when the load actually increases, our latency goes up. So this answers a number of questions all at once. We can see the maximums and the outliers. We can see generally where the average is. We can also see more detail on the distribution, like in this case where there's fast queries as well as slower queries. So that's particularly useful, and I've explained there, x-axis is time, y-axis is latency, and so on. Not only is that distribution great, it's also efficient. So DTrace is grouped in. DTrace, when it runs inside the kernel, to create those distributions, it groups data into buckets that span the distribution, quantize the data. Doing that in the kernel is doing it at the point of collection. That's efficient because what happens is these summaries, so a summary is a column, a 1 second column that is already, it doesn't contain all the events, it contains the quantized or pixelated information. These are read by a userland program at a gentle rate. For DTrace, by default, that's 1 Hertz, which is the switch rate. DTrace can then ioctl the kernel and read that information just once a second. That is part of the design of DTrace that makes the performance impact minimal. So this is absolutely not like how other tools perform. For example, if you're sniffing packets, depends on the implementation, TCP dump or snoop, if you're sniffing packets, for example, and you'd like to come up with some sort of representation or visualization, for TCP dump, each packet is passed from the kernel to userland, and there's overhead to do that. It is a context switch from kernel to the TCP dump userland process. It has to copy the data from one memory address space, the kernel, to userland, so there's MMU work and cycles there, the memory management unit. Doing that for every packet when you could be doing 100,000 packets a second can really slow things down. Tools like TCP dump deal with it by dropping packets and letting you know that it's dropped them. But the performance overhead of running that is substantial. DTrace is similar in that we're getting information from the kernel, like TCP dump is getting packets from the TCP IP stack. However, DTrace is summarizing it inside the kernel first and then passing these summaries only once a second, or it's tunable, once a second down to userland, where it's then processed and turned into a visualization like this. That's part of why DTrace does have very low overhead. There's certainly overhead when you turn on DTrace. It's not completely free, but it's been very carefully designed to minimize that. So distributions like this, DTrace is very good at, because it can basically, in the kernel, pass us a column each second, and it's already done that summary. So MySQL query latency is what I'd like to talk about in detail. This is something that many customers are already considering and looking at because MySQL has the slow query log. The original slow query log, it was useful, but it only tracked queries that were 1 second or longer, which was too coarse. That was fixed with the microseconds patch, thanks to the Percona guys. Looking at query latency is a good starting point with DTrace. And in fact, if you're on a system that doesn't have the microseconds patch, it's fairly trivial to go and fetch query latency at whatever resolution you want from the internals of MySQL. With query latency, you can build upon it to include and compare other components. Like I said earlier, it's ideal to be able to express things in units of time because you then can compare them. Distribution plots, like we saw with the previous heat map, can reveal details that aren't visible from the slow query log. You can also fetch MySQL query latency either from the MySQL user statically defined tracing provider, USDT, or the DTrace PID provider, which does dynamic tracing if that's not.